All right, I'm pleased to introduce June and Chris from Princeton University, and their primary talk is going to be about software-defined border routers on their campus. And then I also heard a rumor that if there's extra time, June may be able to talk a little bit about some of the work he's been doing with his Globus installation. So I'll turn it over to June, and he can get started.
Hey, thank you, Jason, and thank you for giving me the opportunity to present here, the CI Brown Bag. So hello, everyone. My name is Jun Kim, and I will present our work at Princeton University, which is titled The Software-Defined Border Router on Campus. Chris Tengi is my manager and co-worker of this project, and he should be online to join the channel, I presume.
Yep, I'm here.
Cool. So first, I want to mention that I have already presented this work at Internet 2 TechX, which was around 1 or 2 months ago. So some you may have already seen this. And there were no big changes since then, but Jason and I still thought that this might be new to some folks and it'll be worthwhile to share. So we'll give this talk. This is not a long talk. I expect it'll take around 20 to 30 minutes to present, and we'll take questions after that. And yeah, as usual, this is quite informal. Let's see, like if time permits, yeah, I may talk a little about Globus usage statistics, things we worked on, and I would be interested to hear what other people do to monitor their Globus usage or data transfer usage. Okay, so let's get started. Okay, I don't know why this is. Okay, cool. So I want to start with clearly defining what a software-defined border router is. What you're seeing here is a traditional BGP border router, of course. The router talks eBGP, and it will exchange routes with the external ISP you have. It will update the forwarding table based on the routes it learned and advertised. And of course, all of this will happen in a single box. So in this talk, we'll define a software-defined border router as following. Basically, the part that talks eBGP will be pulled out of the box and exist as a separate component. It'll still talk eBGP, so it'll exchange routes with the external ISP, so nothing has changed there. Nothing has to change on the ISP side. And now this new BGP component will update the forwarding table in the switch remotely. And as you can see in this architecture, the control plane and the data plane are separated, and that's why we call this a software-defined border router. And of course, the interesting part is here, where you can stick some interesting software piece that can possibly customize the forwarding table to meet our needs. So before I really dive in, I want to cite some previous related work on this subject. In 2005, there was a paper in NSDI titled The Design and Implementation of a Routing Control Platform. And I thought there was a really interesting statement here, which says, RCP is a logically centralized platform separate from the IP forwarding plane that performs route selection on behalf of routers and communicates selected routes to the routers. So I thought this really kind of rings the bell of SDN and stuff. This work was not really SDN because this RCP was using iBGP, but I think this is one of the earliest works that try to have a centralized platform and a software that would determine how traffic should be routed, or extending what normal BGP would do. Route flow is a more recent work. It was between 2010 and 14, I think. One of the first works that used open flow switches as forwarding devices, while a separate route flow server will reproduce the whole topology running VMs and push rules to the open flow switches to do routing. Atrium is a more recent work, a well-known project from ON Lab. I think ON Lab is now part of ONF. This work focused on interoperability, creating a single control platform that would work with hardware devices from multiple different vendors. And it'll program these bare metal switches using OpenFlow 1.3, and it was running Quagga inside. So this idea is quite similar to what we have at Princeton. The goal of this talk is we will share a deployment experience, of course, and then ignite discussions about doing things differently, and then want to talk about possible applications and future plans we have with our software-defined border router. The outline of the talk is we'll first briefly talk about, show how our Science DMZ looks like in our Princeton University environment. And then we'll share our experiences of software-defined border router deployment and extension and applications, and I'll take questions after that. All right, so this diagram shows our network in a very high level. Our primary connection is at our campus border router on the right. We have two connections, two research networks, which is Internet 2 and ESNet. Our commercial internet comes from Cogent and Hurricane Electric, all connects to the campus border router. We have an IPS/firewall between the campus border and campus core. And of course, the rest of the campus network follows the campus core. The interesting part is this second connection we have with the Internet 2, which is also a 10 gig connection. And this is where our Science DMZ border router connects to. And this border router advertises the Science DMZ subnet we have. And then this is followed by the Science DMZ core, and then our network sits behind that. And of course, this Science DMZ border router is software defined. So we'll and this talk will be about this part. This is just a photo. So I like showing real photos because it kind of looks real. So this photo shows our actual software-defined border router in our rack. It is a Corsa DP2200 switch. You can see the yellow one is our Internet 2 connection, our second connection to Internet 2. The connection right next to that is traffic that goes to the controller VM, this is all BGP traffic that goes to the controller VM. And the connection next to that is to our campus, which is the Science DMZ network. So the data actually just goes through the Internet 2 and the campus, and control and BGP traffic will go to the controller VM here. I'll talk in more detail in the following slides. Okay, so I'll use this diagram to describe how our router kind of works in a very high level again. As I mentioned earlier, the control plane is now a separate component. So we actually have a virtual machine, which has two software programs running, one is Quagga, and one is this thing called Corsa Routing Adapter. So Quagga is a software program and a routing protocol, and it implements all these routing protocols, including BGP. And when BGP traffic enters the Corsa DP2200, the switch will identify that and forward it to the VM, which is running Quagga. So Quagga will run normal BGP and create this routing table, of course. And then the Corsa routing adapter will take this as an input, parse it, and then create corresponding OpenFlow rules, and then push it to the OpenFlow tables and groups in the Corsa DP2200. And when it does this, it uses this driver called libfluid, which is a ONF OpenFlow driver. So this is how BGP traffic and OpenFlow rules and OpenFlow traffic goes through. When data traffic comes in, the data traffic that is not BGP will not be forwarded to the control VM. Instead, it will just follow through the switch, following the rules in the switch, and traffic will just traverse between the Internet 2 and our Science DMZ network. This diagram shows the forwarding pipeline in the switch in more detail. So this is the whole thing in the switch itself. As you can see, there are 4 different flow tables and 2 group table entries here. So this is kind of like a logical, the outs and ins are kind of logical, so I try to make it more understandable by putting some port numbers there, like for example. So when a packet arrives as a switch like this, it will either come into port 1, 2, or 3. if it's a BGP traffic, first it'll hit the table 0, and which adds a default output action based on the physical topology. So if it's coming to port 1, the default maybe go to port 2 or 3. When the BGP traffic comes in, table 1 and 2 will have some MAC-based and L3, L4, ACL-based filters, and then it actually identifies that this is a BGP traffic. And based on where the traffic came in, it'll actually forward that BGP traffic either to the Internet 2 or to the VM, which is running Quagga. So that's how the BGP traffic is dealt with in the switch. So traffic which is not BGP will actually go through table 012, but it'll actually not be identified as BGP, of course. And then it'll actually hit table 3. And this is where it gets really interesting, because table 3 is the one that has the prefix matching table, which you will normally see in a BGP, any router actually, right? So currently this table 3 holds about 17,583 prefixes, and based on the destination prefix, it'll either forward to 0 or group 0 or group 1, and group 0 will forward it to Science DMZ, group 1 will forward to the Internet 2. When I talk with Corsa, the size, we get a lot of questions of how big is this table 3, and what I heard from Corsa is that actually it's big enough to hold the whole Internet routing table, and it can also hold the whole IPv6 routing table. So it's quite big enough, and it's also kind of customizable. So that's one thing, something good. So of course we did some evaluation whether this is okay or not to do in terms of forwarding performance, control traffic load, and reliability. So first about forwarding performance. This is a screenshot from a graph from our persona measurement archive. So it shows the throughput and packet loss and latency measurements between a persona node we have in our Science DMZ and to UPenn, between us and UPenn. From the middle, before is on the left side, where before we had the Science DM software-defined border router. After, of course, the right is after. And you can see the throughput doesn't change before and after the deployment of the software-defined border router. It's getting 10 gigabits per second without any problem. And of course, latency kind of looks okay, same, and no packet loss. So the takeaway of this slide is just like there's no actual negative impact when you're running. In terms of forwarding performance, there's no negative impact on when deploying a software-defined border router. Okay, in terms of reliability, this is another screenshot just for a month. So this is even up until now, it kind of looks like this. We've been running this software-defined border router for now, I think 5 to 6 months, and throughput is quite stable, no big packet loss, and latency is also kind of stable in that way. So in terms of reliability, it's quite good. Of course, this is another thing that we kind of do some tests about actual doing bulk data transfers. We have a test DTN behind in the Science DMZ, so we do some regular tests. Sometimes we actually do real data transfers for our researchers using the test DTN because it has a better performance. And yeah, everything works fine here too. Next is evaluation on the control traffic load. So just to recap, if you're running a software-defined border router, as I said, the control plane is separated out, and you have this additional overhead because the BGP traffic actually has to go to a separate VM, and also the VM has to use OpenFlow rules and push them up to the actual switch. So this is extra overhead when you're running this architecture. So we want to make sure this is not that big. So we did some evaluation on this part too as well. So we actually did a packet capture of the BGP traffic between the switch and controller. And this is when the software-defined border was just getting up. You just started. As you can see, left one is the time sequence graph of the PCAP, and right is the throughput. So when you turn on the software-defined border, you can see that there's the initial climb up of traffic, as you see on the left. And also, if you measure the throughput, it hits about 200 kbps max. And it kind of only starts at the beginning. There's a lot. And as you can see, I don't know whether you can see it on the right, but there's little bumps going on also, which is like normal updates going on. So as you can see, the overhead is not that big. This traffic is not that serious that you should be able to handle this. Next is another evaluation or analysis of the PCAP capture of OpenFlow traffic between the switch and the controller, because this is another overhead. As you can see on the left, you can see a lot of startup packet going back and forth between the switch in terms of OpenFlow traffic. On the right, you see the throughput. You can see it kind of max around 5 Mbps. 5 megabits per second, which is again not that serious. And as you can see, it kind of only happens at the beginning, because this is when it has to install these rules, prefix matching rules. But after that, it's nothing is actually there. And even the peak of 5 Mbps, you should be able to handle that. And I'm saying it's quite negligible. Okay, in terms of reliability, so this is a big question, and of course a very valid and serious thing to think about. What if the controller dies? And in terms of data forwarding is not disrupted until there is a route update, of course. That the other side realized that our control BGP is kind of dead. So the BGP session will be disrupted after a timeout and until recovery. So the big thing is recovery. And recovery time will really depend on the VM migration time from data center 1 to 2. We actually have 2 data centers, and as I said, our control thing, Quagga, and all that stuff is running in a VM. And when we asked our VM expert on campus, he said that it should take about a few minutes to actually realize the the VM died, and to reignite it and revive it in a second data center. So we think that's not that serious. We heard there's some good technologies from VMware or other things that will make this much faster. So if you're interested, you should look into those as well. So why are we doing this is the big question. The crux of it is, of course, like, why are we separating the control plane and the data plane? I want to actually say that there are some downsides, of course, because we're kind of adding complexity here, and because we have more components, and there's more failure points. But there are certainly some upsides, and just to list some of them, it's easier to add customization, it's easier to innovate, we have less vendor lock-in when we do this, and less hardware dependent. And we do this because we think these outweigh the downsides, which were mentioned here. So I said it's easier to add customizations and it's easier to innovate. So I thought I will just use the last few minutes about applications and extensions we had or can have with our software-defined border router. So before I actually go into that, I want to mention that our hardware, which is of course DP2200, allows us to create multiple instances or virtual forwarding context, they call it. What it means is that you can slice the switch and assign a group of ports to that virtual forwarding context, or VFC. And you can create another one with different set of ports and call that VFC2 and so on. And depending on that VFC type, you can actually assign different hardware resources. Like you want to have this much of memory, and et cetera, et cetera. So it's quite versatile and it's quite flexible in terms of that. And each VFC can actually connect to a separate controller if you want. So the first application I want to mention is the IP table-based firewall. It's quite interesting. This work is actually from Dr. Philip Papadopoulos from UCSD. And I reached out to him, and he had an undergrad, I think his name is Brian Greenberg, who was working on it, and they were kind enough to share the code with us. So what I did was I just used their code and run this controller. And this application is very interesting. It allows you to write a firewall rules in IP table rules format. It's quite cool. So a lot of system admins who take care of their servers know IP table rules better. And it's kind of hard job for sometimes to actually translate that into access control lists for switches and routers. So what these things allow you to do is you can actually route these access control lists as IP table rules and just feed it, run it as a controller. And this application will push that and theoretically make a L2 firewall based on those IP table rules. It's still a stateless firewall, but it's I think is a really good thing. And you can actually just right there create an open IP table-based low-impact firewall, just like that. And we actually have this running in our environment in front of our L3 BGP routing application. And it helps us secure our persona nodes and data transfer nodes in our Science TMZ. The second application is dynamic bypass. So we actually have an application that will actually automatically bypass Globus data transfer traffics and remove the bypass when the transfer is done all automatically. So a lot of people have this, like they have a security middle box, and we can say that the default behavior is to go through the security middle box and then to the Science TMZ, or there's any network. And then what we do is actually we have a data transfer node with Globus, and we have a hooks to it. And it'll listen to any event like start of or end of a transfer. And then when it sees it, it'll send a call to our VM, which knows where the data transfer is happening, the source, the dest, and the ports. So it'll install a rule dynamically so that it'll make a bypass rule so that the traffic of this data transfer will bypass the security middle box. And the cool thing is when the transfer is done, it'll also send a notification to the VM, which will move the bypass. So we had this running. I think right now we don't have it running because we are doing some more testing, but this is quite a cool application we have with our software-defined border router. I think, yeah, so it's kind of something similar what SidePass I think will do. They also have some similar stuff going on, I think. The concept is quite similar. Application 3 is BGP SRX. So it was interesting. So the National Institute of Standards and Technology, or NIST, actually had a project where they actually add a piece of software to Quagga so that it can do BGP-SEC path validation and RPKI route origin validation. And all of this is open source, and you can actually just download it. And when I saw this, that was cool. I thought it was really cool because the software-defined border we're running is also running Quagga. Maybe we can just run this so that we instantly have BGP-SEC path validation and RPK route origin validation, which we should all try to have. So when I looked into this, I realized that our good friends in Juratech already kind of did this, tested this. They actually integrated with and tested it with the Corsa routing adapter. And this work was from Brian Lebenick, who was at Juratech at the time. I think is USMA West Point right now, and Sean Donovan and Russ Clark from Juratech. And they said it worked really beautifully. And you actually have BGP path validation, RPK, route origin validation by just running this. So Princeton don't have this yet, but we are looking into integrating this, and this is our next target to do. This application 4 is about BGP anomaly detection. This is also in our plans. In 2004 or 6, there were really good work on detecting BGP anomaly. And most of these these are actually softwares, right? It'll look at the BGP updates and some publicly available information and see whether the incoming updates or BGP things are fishy or not. So, I also found out that one of the software called Pretty Good BGP, their stuff is implemented with Quagga. So, and the software is still available, so you can just download it and use it. So I thought, like, okay, this is cool. We can actually integrate with our software-defined border router, send our BGP updates to this analyzer, and maybe it'll find some anomalies and set some rules and do the updates on the forwarding table based on this analysis. So this is another cool application we have in mind. The last application we have in mind is route optimization. So this kind of works if you are kind of multi-homed, and we are not yet, but we hope we do later. So our border router, let's say your border router is connected to multiple ISPs, and you are running a software-defined border router, and you actually have the route optimizer. What you can do is, because this is all open flow table rules on the switch itself, you can kind of fiddle with it so that some traffic, for example, some video traffic will use a different ISP. Bulk data transfer will go to another, like for example, Internet 2. Some latency sensitive traffic you will forward it to another ISP, and kind of do some customization like that. This is not the complete thing because you only have control over what's going out. That's how BGP kind of works. Not totally control how things will come into your network, but at least you can control what's going out of your network, how things will go out of the network. So I thought this is another interesting application we can work on using our software-defined border router. All right, just to summarize, Princeton deployed a software-defined border router in a semi-production manner. We've been running stable for several months now, I think 5 months or 6 months now. We have Sonar node and a data transfer node running, and we also have some additional custom application running. For example, the IP table-based firewall application and the automatic bypass for bulk data transfers. Some future plans, we will continue to run and maintain this infrastructure, and we're trying to add more hosts to our Science DMZ network so that it grows. And we want to implement and apply some the aforementioned applications, starting with the BGP SRX, which will give us path and origin validation. So some lessons learned. So running an SDN solution is not hard. I would really want to say that. And please try to start with what you are familiar with. For example, the BGP configuration with the Quagga is quite simple, and everyone will find it not hard to do. start deployment on less mission critical services. We were kind of lucky in that because we had a second internet to connection and we had a small SANSD subnet to start with. So whatever we did not kind of disrupt the actual campus network BGP sessions. So that was good. Maybe other institutions can find similar methods or way to do this. And so when you do this, try to prove its stability and focus on its benefits. And of course, try to get commercial support if possible. And thank you for listening, and I'll take any questions.
All right, thanks a lot, June. So we've already had a couple come in. The first, I guess, is more of a statement from Michael Sinatra. If you follow course's recommendations, the table won't be big enough for both IPv4 and IPv6. You need to create a bigger L3 table than what they recommend because he has personally managed to overflow that. So.
I see. Yeah, so I never tried running both. Yeah, what I heard was like it's big enough to run the whole IPv4 table. And then separately, IPv6 it can hold. Not sure if it can run both of them at the same time, but as Michael Sinatra said, you may have to do something special there.
And his second one is a question. Do you see application 1 and application 3 as advantages, given that most black box routers just do those functions as part of their integrated UI without the need for other controller functions?
Okay, so let's try to, I don't actually remember what 1 and 3 is. I see what you mean. So 1, let's see, are there things that actually allow you to write rules as IP table rules?
Well, June, this is Chris. I don't think the issue is really the syntax that you use.
Okay, yeah.
As much as the ability to do the function. And the key that I see here is that while integrated routers have this functionality, what they don't necessarily have is the ability to do other things as well.
Mm-hmm. Yeah.
Any given router might have a certain set of applications, but if you just want to go do your own, it's like, hey, wouldn't it be cool if we could do this? In most cases with a commercial router, that's a little more difficult.
Yeah. So,
Sorry,
of course.
Michael, I don't know IP table syntax myself. I'm an ACL guy.
Yeah. I mean, like, there's no like clear winner about which syntax is better. I guess like some people like this, some people like that. But I think, in terms of the actual function, application 1 is not a shining function or really a shining application, but it kind of just shows like you can do it differently, easily. With
just to follow up on that, this is Michael.
Yep.
For us, it was actually kind of an obstacle for deploying this, that you couldn't manage ACLs and routes with the same effective controller interface. Like you had to run Quagga and then run something else.
True. Yes.
Manually add open flow tables. So that was actually kind of a minus for us, to be honest with you, in terms of how we scale and deploy this. So
the reason that we did this was because we had the same issue. We wanted to implement ACLs so that we could limit the traffic to, in our case, Globus transactions. And there was no other way to do it. I would have preferred ACL syntax because it's what I've been doing for almost 30 years. But this was the tool that was out there. Could we rewrite this and have it accept ACL syntax? Sure, that's possible. Mm-hmm. Would we want to have to do that? We'd prefer not to have to, but if you need the functionality and you're trying to get the flexibility of having the OpenFlow-based platform, we're kind of stuck in having to go down that path. But I don't really see it as stuck because it gives us other flexibility that you wouldn't otherwise have with commercial products.
Yeah, but I agree with Michael in that sense. Like, you have separate, 2 separate controls doing this. You rather have one single place to do, BGP routing and kind of like these ACL things. So, that's good feedback. About 3 was 3. Sorry.
3 is origin and path validation, which.
Yeah. Well, yeah. I mean, I thought like some routers already kind of do this if you kind of do this, right? But I thought like you know, yeah, I would say like this is also this is a basic function what a router can do, but maybe you have your own customization on these things and you can do it. So yeah, I would say this is not also not a shining one. I would say I actually personally like the later ones, like 4 and 5.
All right. Jim Warner has a question. He has heard from Cumulus that they are recommending free-range router as an alternative to Quagga. It's a fork from Quagga. Is this something that you've followed?
Yes, yes. And you know, when I talk with Corsa, they are following it too. They know this is happening. So we may see a different version or a better support happening.
Okay. Yeah. So no other questions, but I have a couple here that I jotted down. I guess my first question is sort of a security and a protection question. Have you done any sort of trials or attempts to try to really knock that thing offline? You know, for instance, how protected is the VM that's running this? You know, seeing as though that's probably one of the weaker links right there. Yeah. And if you were to knock it offline, I know you were noting something about, you know, the only time that this would really disrupt the data plane is if it happened to occur at about the time of a regular route update. You know, yeah. What sort of impact would that have on you guys if that happened?
If the controller goes down, basically, right?
Yeah.
So we actually didn't really do stress testing or try to really break the controller VM in terms of, and because the controller VM itself is using an internal, it can only be accessed internally and through several, there's some ACLs and stuff that
it's on RFC 1918 address space.
Yeah, so only authorized people within Princeton can access it. So it's all password, all protected security wise. So in terms of security, I think we didn't do anything in addition to that because we think it's quite secure in that matter.
Stress testing is a good idea, and it's one of the things that I think we should be doing before we actually try to make this really production.
Yeah. So I think we should try to do more testing in terms of that.
Okay. And at one point, you had put up sort of the load that the VM was dealing with, trying to do all the route updates and stuff like that. Yep. I didn't see a CPU graph or a memory compression graph. I mean, are there either of those things a factor for this, or is it able to keep up?
That's a good question, and we did actually monitor that. I guess more concern is so there's CPU memory on both sides, the switch itself and the VM, right?
Mm-hmm.
I guess, maybe we should do that. We should try to monitor VMs. I'm more concerned of the VM CPU and memory consumption. I think the switch is okay in that sense. But yeah, that's a good recommendation. Maybe we should do some testing on how the CPU and memory copes with this update. Yeah, good feedback.
Okay. And we don't have any more questions coming in, but I do have another one. So why Corsa? Was that really just the only thing that met your needs at the time, or was that what you went with first?
At the time, it was only Corsa.
We were looking for something that had a lot of buffering.
Yeah, a lot of buffers.
And we had heard that one of the national networks had bought a bunch of them, and it sounded like it might be an interesting product to take a look at.
That is true. that there are a lot of white box options that are out there now, which was kind of what I was getting at. Have you thought about any of those or no?
We would certainly be interested in testing against some of the newer boxes that have more memory, but when you have wide area, high latency elephant flows, that's one of the concerns. And
I guess last time,
850.
last time I looked at white boxes, that time it was quite time ago though. But there were plans of making white boxes which has really big buffers. But the time when I was looking, there was not much. I don't know now if anyone knows if there's like white boxes with really big buffers, not really big, but marginally big bug first, please let us know. We're going to look into that too.
Well, I think there's this web page that you can look at that has a lot of that stuff, right?
Oh, yeah. I think he posted the question too. Oh, no, the comment?
Yes.
Yeah, Jim's on the line if you want to interrogate him.
Jericho chips from Broadcom have the ability to have over 10 gigs of buffer memory with the newest chips.
Okay.
Thank you. That's very useful to know.
So are they out? Like you can buy it now? Or?
Yeah, they're the same chips that Arista is using in their 7280s, and I think Cisco's using them too. I don't know who else.
I see.
Yeah.
Cool.
All right, so I think that's probably it for questions. We still have a little bit of time if you did want to talk at all about your Globus work as well.
Yeah, I think there may be a Globus person on Zoom right now too.
Greg is on.
Yeah, so I was wondering, I think I mentioned this one time somewhere, or maybe I sent an email. We have Globus. This is a totally different topic, right? So we had Globus with data transfer happening, but we didn't know how much is being used and how much data transfer is actually happening. You can look at it if you go to globus.org and go through the console, so you kind of catch it. So we thought it'll be really interesting if we actually create some script using the Globus Transfer API to accumulate all the things and create our stats ourselves and put it on some web page. So that's what I did. So we had some interesting stuff. I was wondering how other people do it. I actually today just realized, I think I was late in the game, I just realized today Globus does actually share some summarized stats and some usage reports with people who have subscription. And I saw some really good stuff there, but some things are missing, I guess, because some people want different kind of reports. And I was just wondering how other people do it. I can show what we do, what we have, if that's helpful to people.
Yeah, I'd say bring up yours.
Yeah, okay. So let's see. How do I... Okay. Let's do that. So can everyone see it?
Yep.
Okay. So what we have is called Globus Stats. .princeton.edu, and it's CAS output, so we have to do CAS here. So also a few days ago, I learned that we used to have a long, back to 2016, but just today I heard Globus changed their policy in terms of this. They're gonna only give us 1 month, and I think 3 months of summary from now. It was back in starting December 4th. And because of that change, we only have data up to 2 or 3 months now, I think.
We'll need to change our code to address that.
Yeah, so we have several DTNs. We have actually 6 DTNs, and this shows how much transfer was happening, this graph, right? So just in November, we can see there were 522 transfers total. Our biggest DTN usage is Princeton Tigris DTN, followed by Princeton Neuroscience Institute DTN. And we have some interesting pie charts, where are our targets, non-campus targets endpoints. A lot of things are going to private endpoints. This is how much data transfer is happening within campus, outside on campus, and unknown, which is mostly private endpoints. So we have these interesting tables, number of transfers, number of files, data size in gigabytes, activity stats per DTN pair, how much data, if you can sort by gigabytes, like what's the most traffic is happening between which DTNs. We also have some users there, but which I should not show because it's kind of private data. And you can also select different DTNs because we have multiple of them. They'll give you different stats by number of transfers, files, dataset size, things like that. And you can also set data ranges. So this is what we have. And I was thinking what other people have, if they have anything or have plans, because I would want to see some better tools than what we made, I guess. Or I can work on like improving this. But in general, I was just curious what other people do, because this kind of things could give us an idea like where our data transfer is going to, coming from, how much data is actually exchanged, and things like that. So
I think I asked you this at one point. Is this easily downloadable as a package that you can make available, or no?
Yeah, it's actually already up there. I put it in GitHub, and it's open source. And yeah, this is the, maybe I can share this or someone can share this. This is the URL, and everything is open sourced. I also have a wiki, how to set it up, the steps.
Okay. Yeah, I'd say certainly send that out to the list again, because it may have gotten buried in pre-supercomputing mails. And Greg put into chat that Globus subscribers have access to an endpoint with usage reports for their subscription. There are Excel files with month-to-month summaries and a CSV file with information from the beginning of their subscription.
Exactly. I learned it today. That's cool. I think.
Right. That's what I alluded to earlier when I said we need to change our code.
Yeah. So maybe we are change our code to just parse that CSV file. But this one uses to transfer Python SDK. And I was just wondering what other people do.
Okay. Well, if anybody does have a different approach that they want to share, just type it into the chat room. I could just kind of say that on the ESNet end, we're just using the tools that are provided by Globus for our own internal use. But then again, ours are just testers, so they're not really involved in production data transfer. But we do have a lot of people who probably hit it every single day and every single month from various locations.
Okay. I see.
I'm pretty sure that people from supercomputer centers may have other approaches, since they usually run larger DTN pools. Unfortunately, I don't really see many people on the call today who'd be able to address that.
I see. Yeah. Yeah, I was wondering, like, especially some big places, where there are big data sources. They want to keep track what's happening. And so I was wondering if they have any good tools for doing that.
Okay. Well, I'd certainly say share again on the list, and maybe that'll poke a conversation. But I think that we may not have any comments left here today.
All right.
All right. Well, thanks again to both of you for doing the last talk of 2017. So just as a programming note, we won't have any more. The next talk will be in January, on January 5th, and I've agreed to get Kevin Thompson to give us an overview of the 2018 version of the CC Star program. So happy whatever holiday you celebrate to everybody, and we will talk to everyone in the new year. Cool. Thanks so much.
Thank you. Thank you all.